Good evening and welcome to Stochastic Processes. Lecture 13. So, first let us do a small recap. So, last class, what we were looking at was strong Markov property. And something on a stopping time. We also saw recurrence and transient states. And for recurrent, we saw two different types of recurrent, positive recurrent and non-recurrent. So last class we stopped at trying to calculate the number of returns to a state. So obviously, if a state is recurrent, that means that it will recur infinite number of times. But if it is transient, then it will be something which is less than infinity. But we can find the distribution of what is the number of times that a state returns to the state given that it started from some state. We can calculate the distribution. So we were trying to calculate the distribution. So last class, where did we stop was we identified something known as MJ, which is basically the sum of indicator random variables, which is 1 if at time n you are at state j, 0 if you're not at state j. So you basically add up these ones at each time, ones or zeros, and you get the number of times that you have hit j, or number of visits to the state j. Then we are trying to show, we showed expectation mj given x0 equal to j. This is the summation n equal to 1 to infinity pjj. We're using linearity of expectation and writing out mj as sum of indicator random variables and interchanging the summation and expectation using the property of linearity of conditional expectations. We wrote this. So what is the observation here is if this is less than infinity, then mean number of returns is finite. So you'll have finite number of returns that the expected number of times that you return to the state is a finite number. Actually, we can show this using the Burle-Cantor lemma, that if the summation of n-step probabilities is less than infinity, then j occurs infinitely often with probability 0. So there's no probability that j will occur infinitely often. The mean is finite, then the number of times it will hit the j is also finite. Okay, so now I'll give a statement, which I'll not do the proof because it is a bit time consuming, but I'll give the intuition behind the statement. So now, since we found the expectation of this, we want to find the probability distribution or the probability mass function for this, because mj is a random variable which takes the which can be any natural number. So what we want to do is we want to find the probability of mj equal to m conditioned on x0 equal to j. Right. So what does this mean is, so given that you have started at j, what is the probability that you'll visit xj, visit the state j only m times in the total sample path? You'll not visit j more than m times. You'll just visit exactly m times. So this is given by fjj is the probability that if you start at j, you hit at j once. Next, again, the probability that you start at j and you hit at j. This goes on till m times. And then you have, from then you'll never hit j. So that is 1 minus fjj. So you have fjj whole power m into 1 minus fjj. This 1 minus fjj could also be written as, for the stopping time, probability that t1 equal to infinity given x0 equal to j, where t1 is the stopping time where you hit j the first time, which we discussed in last class. This is just this part. So basically, the probability mass function of the number of times that you hit j, yeah, is just fjj power m into 1 minus fjj. Now from this observation, so you understood the intuition that the it will hit m times if you take each step, and because of Markovity and the independence of the past, you start at j, you go to j. That probability is fjj. Now you have hit j one time. Then again you start at j, you go to j. You have hit j second time. Similarly, continue doing this m times. And then after that, find the probability of not hitting j, which is just 1 minus the probability of hitting j. Okay. So I hope you understood. So now let me give a theorem. This is an easy theorem. So what the theorem states is, suppose you have a DTMC. Except on state space S. And if, okay, and statement one, if J, which is a state, is transient, right? It is a transient state. If Jj less than 1, then where n belongs to 0, 1, 2, the probability that mj equal to m conditioned on x0 equal to j is just fjjm to 1 minus fjj. Because j is transient, we know from definition that the return probability is less than 1. It is not 1. And so this is the condition. Next, 2. If the state is recurrent, if j is recurrent, then we know that fjj equal to 1. So the return probability to j, if you start at j, is 1. Then we get probability mj equal to m conditioned on xj equal to 0. This goes to 0. This is for m belongs to 0, 1. So any number you take in the natural number, the probability mass function is 0. The distribution of this will look something like probability of mj equal to infinity given x0 equal to j. This will be 1. So this distribution, the whole mass actually lies, the whole probability mass lies at infinity because it can't take any point. The probability of all the natural numbers will be 0. It lies at infinity. So from this, what we can state is, suppose now I want to calculate expectation of mj conditioned on x0 equal to j. Then I just need to write uh, over m, and then probability of mj equal conditioned on x0 equal to j. Okay, so now I'll make an assumption. J is transient. So if J is transient, then I'll have and this sum is basically fjj by 1 minus fjj, which is less than. And if J is recurrent, then this goes to it. So which which makes sense. Like from the intuition, this is what we get. So we wanted to find the expected number of times that you hit a state, given that you have started from the same state. So uh, the way that we did that proof is we tried to first find the mass distribution, um, probability mass distribution of the random variable mj, which tells you the number of times that you hit j, right? So we wrote it down in terms of fjjs, which are probability of hitting j, given that you have started at j. Uh, and then we found the probability mass distribution for two cases where j is a transient state and j is a recurrent state. If j is transient state, then the probability um, of hitting m times becomes fjj power m into 1 minus fjj. And if it is a transient state, and if it is a recurrent state, that goes to zero. Because it goes to zero for all natural numbers, the probability distribution lies at infinity. So now we calculated the expectation and conditional expectation mj uh, conditioned on x0 equal to j by just by normal summation of um, m's with respect to fjj power m into 1 minus fjj, and we wrote it out. For transient, we saw that it is less than infinity, and for recurrent, it is infinity. So we also showed last class this A part, how these both are equal. These both are equal by linearity. And then we calculated this part. Uh, Both are the same parts. So, B. So now we have one more claim. So I'll just write down in short what we have seen. So expectation of mj conditioned on x0 equal to j. Right. This is fjj by 1 minus fjj if so. First I write what we did in the last time. So last time this was summation 1 infinity pjj n. Right. This is fjj by 1 minus fjj, which is less than infinity, if j is transient, right? And infinity if j is recurrent. So observation is this: the infinite sum has a uh, con is convergent, and if it is convergent, then the tail sums then the tail values go to zero. So for j, if j is transient, then limit n tends to infinity pjjn equal to zero. So from this observation, we have that if j is transient, then limit n tends to infinity to 0, and if J is recurrent, then summation. Okay, this is what we started last class, and this is the complete analysis for number of returns to state. So this is the whole analysis for to find out the probability distribution of how many times you return to a state, um, if the state is transient, if the state is recurrent, the expected number of times that you'll return to the state. If it is recurrent, then you'll return infinitely often. So the expected number of returns to that state, if the state is recurrent, is infinity, which is obvious, but we showed it properly. And then if it is transient, then we showed that the expected number of returns is a finite number, which depends on the probability that you hit the state at least once. Yeah. So we got multiple conditions for transience and recurrence based on the number of times that you hit. So we'll do another small quick recap on what we usually discuss. So uh, we'll do a recap on communicating classes and class properties. This we saw last time. So suppose you have a DTMC. Except all state space S. So we give two definitions. One is reachable and communicates. So a state I is reachable from J if there exists some number, some natural number, such that the n-step probability of going from J to I is greater than 0. There exists some positive n-step jump from J to I. Then we say that J is reachable, no, I is reachable from J. So what do we say? We say that I is reachable from J. If J is reachable from I and I is reachable from J, if both of them happens, then I and J communicate with each other. Right. And we also showed that this communication is an equivalence relation. So what does it mean when I say that this is an equivalence relation? Is it satisfies three properties. Reflexive. So the reflexive properties I communicates with I communicates with itself. Second one is symmetric. So if I communicates with J, this implies J communicates with me. The third one is transitive. So what does this mean is if I communicates with J and J communicates with K, then this implies that I communicates with, right? So we showed this that these three, if a relation satisfied these three properties, then uh, we called it as an equivalence relation. And communication satisfied this property. We also saw that the communication equivalence relation, it partitions the state space. Right. So here are 2 points from it. So given a DTMC Xn on state S, the communication equal relation partitions the state space S, and each of the state space, each of this partition, we call them as communicating classes. And next we have a definition which we have not discussed before. This is a new definition. So communicating class C. So suppose there is a communicating class C. This is known as a closed communicating class if for all I belongs to C. So for all the states in the communicating class, if you take one state from the communicating class and J does not belongs to C, I'll just pause for 1 minute. Sorry. So yeah, we were discussing when is a community class closed. So community class C is closed if for all the states that belongs to C and all the states which does not belong to C, the communicating class. If I have Pij equal to 0, then we say that community class C is closed. So what does this mean is, if you have a communicating class, if you take any state from the community class and any state from non-community class, then the probability going from that state to that state, there's no way you can go from the state in community class to a state in non-community class. Then that state is known as closed community class. So what does this mean is, if you have a closed communicating class and a community class which is not closed, once you enter the closed community class, there is no way of you going out of the closed community class. You'll always stay inside the closed community class. So I'll give an example for this. So suppose 1, 2, 3, 4. You have 4 states. Okay, I'm just drawing the transition property lines. So probability of going from 1 to 2 and 2 to 1, and also circle with some probabilities, and also 2 with some probabilities. Then you can see that, and if you have from 3 to 4, 4 to 3, and also self loop. Okay, so now if this is your transition probability, transition probability diagram, transition diagram, then you can see that 1 and 2 are a communicating class, and 3 and 4 are a communicating class. Right. So you have some possible probability of going from 1 to 2. You have some positive probability from 2 to 1. You have a positive probability going from 2 to 3, but you don't have positive probability. So once you're in state 3, there is no probability of going back to state 2. So 2 and 3 don't communicate with each other. 3, 3 is reachable from 2, but 3 and 2 don't communicate with each other. Similarly, you have possible probability going from 4 to 3 and 3 to 4. So 3 and 4 communicate with each other. So 1 to communicate with each other, 3, 4 communicate with each other. 1 to belong to a class, 3, 4 belong to a class. Okay. So now if you start in this, so let me call this communicating class 1 and communicating class 2. So if you are at C2, you will indefinitely stay at C2 in C2 because there is no way of going out of C2. So now C2 is a closed community. But if you are in C1, with some probability you can go to C2. But once you go to C2, you're done. You'll be staying in the C2 and C2. Um, so this is how equivalence communication classes partition the state space, and uh, they, you have different types of classes where a whole class will be closed class, where once you go into a closed class, you're done. You can't. The third part is um, P. This is the connection probability matrix. This is irreducible if there is only one communicating class. Or you can also call this the DTMC, or S, the state space is irreducible. The DTMC is irreducible if there is only one communicating class. So if a Markov chain has only one communicating class, then you can say that the DTMC is irreducible. So one of the most simplest cases, you have two states and you have some problem here. So there is a positive probability of one communicating with two and two communicating with one. One communicates with two and there is only one class. So this is an irreducible. You can also have examples where you have infinite states and with some probability go to two, with some probability go to one. Three, two. Right. So everything is community class. So because there is some positive probability from which you can go from 1 to 2. To go from 1 to 3, you have a positive probability path. You go from 1 to 2 and 2 to 3. To go from 1 to 4, you have 1 to 2, 2 to 3, 3 to 4. So this is a positive probability. Any number of states you take, you'll always have probability, positive probability path, which is non-zero number to go from that state to that state. So all the states in this probability in this DTMC are communicate with each other. So they all belong to the same community class. And if they all belong to the same community class And because the whole discrete Markov chain has only one commuting class, this is also an example of an irreducible Markov chain. So these both are examples of irreducible Markov chains. So one more observation is that if a Markov chain is irreducible, then it is closed. So what this implies, a Markov chain is irreducible means it has only one community class. If it has only one community class, no matter, you'll always stay in the community. So that community class is closed. So that Markov chain is closed. So that is pretty evident, and yeah. And all these concepts of irreducibility and communication, the communicating class, they just depend on uh, positions of the positive elements in the transition probability matrix, but not their values. So if you have some positive non-zero number, that would be very small at just the certain places in the transition probability matrix, then you can have an irreducible Markov chain. But if it doesn't depend on the value could be anything. Because I'm just writing out I'm not even writing the probabilities in these transition matrices. So the properties of irreducibility and classes depend on where the probability non-zero probabilities are present, right? So here in this second example, you don't need to have the self loops. So even if the self looping is zero, and if you have a transition matrix which just goes 0, 1, 0, so on, okay, and 2, 2, 1. This is some p 0, 1 minus p 0, 0, 0, 0. And then you have 0, p 0, 1 minus p 0, 0, 0, 0. 0, 0, p 0, 1 minus p 0, 0, 0. So if you have a matrix of this form with the correct positioning of non-zero probabilities that p and 1 minus p could be anything, you'll get a irreducible closed Markov chain. So it depends on the positions of non-zero values of the transition probability matrix, transition probabilities, but not on the precise values. The values could be anything. It doesn't matter, right? Yeah. Next again, I'll just go theorem. So if state j is recurrent, that is fjj equal to 1, and we also have fij equal to 1, then we can write where this gamma j equal to 0 if j is null recurrent, and is greater than 0 if j is positive. So if j is recurrent, we know that So if J is recurrent, we know that uh, limit n tends to infinity, summation equal to 1 to n, E j j k goes to infinity, right? This theorem, what it states is if J is null recurrent. So now this theorem, it just says that if J is null recurrent, then summation k equal to 1 to n p j j k goes to infinity slower than n. And if J is positive recurrent, then the same term grows to infinity proportional to k. So this gives the rate at, so if J is null recurrent and positive recurrent, this summation goes to infinity. But what is the rate at which that goes to infinity? That is what this theorem gives. This proof will not be doing. Okay. But we'll remember this theorem because we'll be using proving something else. So for null recurrence, it means that the rate at which the mean number of times you hit a state, it goes to infinity, but at a slower rate. If it is positive recurrent, it goes at a faster rate. Okay. In the recap, we also saw class property theorem. So the class property theorem states that um, the states in communication class are either all transient, two, all null recurrent, or three, all positive. We did the proof at this one of previous class. So what does this mean is if you have commenting class, then transients, recurrence are class properties. So if one of the states will have this class property, then every state will have. So in this commenting class, if you want to show that something is transient and recurrent, it is sufficient to show one of the state is transient. If one of the state is transient, all the states are transient. One of the state is null recurrent, all the states are null. So we did the proof for this in these classes. Okay, so next we'll go into something uh, yes, positive recurrence and invariant probability vector. So from now on, what we'll do is we'll just look at closed communicating classes because the, so So the intuition behind this is, suppose you have an open communicating class and a closed communicating class. Then what happens is, even if you start at an open communicating class, with some finite probability, you'll always, with some non-zero probability, you'll always end up in the closed communicating class. So if you have a Markov chain with two communicating classes where one is open, one is closed, it is always the steady state, or as n tends to infinity, the 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 behavior of the total Markov chain will resemble the behavior of the Markov chain of the closed communicating class. So let us take in this example where you had C1 and C2, two communicating classes. So even if you started communicating class C1, then after some time you'll always end up in the state 3, 4. And then if you just know the behavior of the states of 3 and 4, you know the behavior of limiting behavior of the whole Markov chain. So mm, we only need to look at closed communicating classes for any Markov chain. So what we'll do is uh, we'll just study from now on, we'll just study irreducible DTMCs. If it is irreducible, then it will have only one communicating class. And if it has only one communicating class, that communicating class is closed. So we'll just look at irreducible DTMC, because now we're going into that uh, study of limiting probabilities and invariant distributions, where you don't need to look at open communicating classes. It is just sufficient to look at closed communicating classes. Okay. So first, so let there be a DTMC. So you have a DTMC except now this DTMC is irreducible, right? So now this is positive recurrent if and only if there exists a probability mass distribution pi on S such that pi equal to pi p. With pi I greater than 0 for all I belongs to S, and such a pi is unique, right? So this is the theorem. Theorem says that if you have an irreducible DTMC, then if the DTMC is positive recurrent, then you'll have a probability density mass density vector pi such that pi equal to pi p, and that pi is unique. And also, if you have a probability mass distribution pi, a vector whose sum goes to 1, such that pi equal to pi p, and that pi is unique, then you can say that the DTMC is a positive recurrent DTMC. That irreducible DTMC is a positive recurrent DTMC. So before proving the theorem, we'll just talk a little bit about some remarks. Right. So first, this is a matrix expression. So pi equal to pi, where pi is a vector, p is a matrix. Right. This is matrix expression. Now what we see is pi is basically a left eigenvector for p. Right. So now what this matrix equation does is it yields one equation for each pi j. So I can write pi j equal to summation of I belongs to S by J Pij. Sorry, by I Pij, right? So basically what this is this is a dot product between pi and jth column of P. The theorem which is stated here, this theorem, asks for positive values of pi j. Now, let us see one thing. So our observation is that E is a stochastic matrix. Right. And we know that one of the eigenvalue is 1. Okay, so just one small example for this is, so suppose you have a stochastic matrix P11, P12, P21, P22. We know that the row sums up to 0. So if you multiply this with a vector 1, 1, then what you get is P11 plus P12 and P21 plus P22. This is basically 1, 1. Because P is stochastic matrix, the row sum is 1. Okay, so what you get is P into the vector 1, 1 equal to 1 into, therefore 1 is an eigenvalue, right? And 1, 1 is an eigenvector. Okay, is the right eigen. But here we are trying to find the left eigen. So pi is the left eigen. This is the first remark. Okay. Next, if pi equal to pi p, we can multiply with p on the right hand side, right multiply. Then right multiply with p on both sides, right? Because P is a matrix, it is important, and matrix multiplication is not commutative. It is important to see at what side you're multiplying, because A into, if A and B are matrices, A into B is not equal to B into A. So you need to be careful on which side you multiply. So we're multiplying on the right hand side of both the sides of the equation. So we get pi p equal to pi p into p, which is pi, because pi p equal to pi, and pi p into p is p square. If we keep on continuing this recursive equation, we get pi equal to pi p power. Sorry, this is not bracket and this is just power. C. Pi equal to pi p implies pi equal to pi p power n. This is what we saw in the previous case. So now what does actually pi mean is probability of x0 equal to I equal to pi I. This is the pi I. This is the transmitter. Similarly, from this we get probability of xn equal to I is also pi I. Hence, the pi that we are searching for, the pi that we are searching for is an invariant distribution or invariant probability vector of the DTMC. So what does this invariant distribution or invariant if your initial distribution is invariant, you will always have the same invariant distribution, right? You always have the same invariant distribution. This implies that the DTMC is a stationary process. Okay. Since P is irreducible, and we have pi equal to pi p with pi I greater than 0 for some state, right? Now consider a state J, another state J, which belongs to the state space. Since P is irreducible, so I and J communicate with each other. Because it is irreducible, there exists only one commuting class and they both communicate with each other. Therefore, there exists an m greater than 1 such that Pijm is greater than equal to 0. Now, what does this mean is there is some positive probability you will go from I to J in m steps, right? So pi equal to pi p power m. From this equation, get that pi j equal to summation of L belongs to S pi L p L j m. Now this whole term will never be 0 because you have pi I which is not equal to 0 and you have p I j m which is not equal to 0 from the irreducibility, right? So if P is irreducible and you have a vector pi equal to pi p such that only some states pi I is greater than 0, then all states pi j greater than 0. So for all states it will be greater than 0 just because P is irreducible from the condition that P is irreducible. So in this theorem, it is just sufficient to show that, sorry, part 2 back. So if pi equal to pi p, from the irreducibility condition, we can see that pi equal to 0 for all I belongs to S, right? This condition is satisfied. But existence and uniqueness need to be shown. But if we show existence, and if we also show that only some states are positive, it implies that all the states are positive because P is irreducible. One more remark is this theorem applies for irreducible positive recurrent DTMC, right? So if the Markov chain is irreducible positive recurrent DTMC, so if it is irreducible positive recurrent DTMC, then what happens is the pi I is less than infinite. And so this can be normalized to get a unique pi. But if it is irreducible and null recurrent DTMC, then there is no guarantee that summation I will be less than infinity. It may not, it may not, it may go to infinity. So they're not summable and they'll not be unique. We'll see this later. Okay. So next we'll do the proof for the theorem, right? So we'll do the case where Markov chain is irreducible and positive recurrent, implies there exists pi equal to pi. Okay, so first we have assumed Markov chain is irreducible and positive recurrent. So we select some s greater than equal to 0, which has nothing to do with state space, which is just a type. We set is equal to probability of xs equal to 1. So s belongs to the time and I belongs to the state space, yes. Okay, now we define two terms. Bn, which is basically 1 by n summation as. So now here as, this is a vector. It's a vector of all the a's. So as is basically a1s, a2s, so on. And similarly, we define Cn. So from Markov chain property, we know that A is equal to APS, where AIs are basically initial probability. So probability that you start at I. AS is the probability that you are in state I at the S step. So you to get to S step probabilities, you take the initial probability and you multiply the transition matrix to the power S times, you get there. So since A is equal to this, we replace this in the equation 1 and we get APS, right? Now A doesn't depend on the summation is a mess. A doesn't depend on us, so we can take this out. So now as you can see, since A is a vector, here B is also a vector, right? Similarly, this whole thing, this whole thing is a vector equation. So I'm writing out just one part of the equation. So I'll take the jth component of it. Pjn equal to summation I belongs to S. Ai 1 by n summation S equal to 1 to n Pij S. Now this we have seen today is basically the theorem that we studied before, but we have not done the proof for, is this term. As limit goes to n, we know that this goes to gamma ij. And for since now we are looking at positive recurrence, this is something positive, which is not zero, right? So I'll take the limit on both sides. Now what we'll do is we'll exchange these two, but the exchange of limit and summation depends on some things. We need to for sure that the limit actually exists to change this. So we'll use the theorem known as bounded convergence theorem, but we'll not prove that this is bounded here. But I'm just telling that the bounded convergence theorem helps me to interchange these two. So now I'll have I limit n tends to infinity in summation s equal to 1 to n Hjs. And now this limit, I know that this goes to gamma. Gamma j doesn't depend on I. So this is gamma j summation I belongs to s here. This whole term sums to 1 because these are just probabilities. The AIs are probabilities. So the AI vector, this sum is just 1. Since these are also probabilities, these are just the uh, average of probabilities. This also will be a probability. So this will go to gamma. Now what this says is in the vector, all the jth term uh, component of bn's go to gamma j. So limit n tends to infinity b equal to gamma, where gamma is a vector, gamma 1, gamma 2, so on. So now we claim that let pi equal to this gamma, right? And we have Cn, which is a1 by n, summation equal to 1 by n, p power s minus 1, right? Following the same steps above, we see that limit n tends to infinity, Cn is equal to pi again, right? The same steps. It will be gamma, but we're assuming that gamma is pi. Now, we also know that from definition, right? From the definition, from these two. From 1 and 2, we have Pn equal to Cn into P, right? Now we take limit on which is pi equal to pi. So we have shown that there exists a pi such that pi equal to pi p using irreducibility and positive recurrent. If it was not positive recurrent, then you won't get the limit to gamma here. Okay, now all we have left to show is summation pi j is 1 and pi is unique. So we need to show these two things. So for the first one, I'll just give a hand wavy intuition of y summation pi I j. Since we started working with probability distribution functions and we took the averages of probability, the limits of the averages of probability distribution functions should remain a probability distribution functions, hence summation of pi j equal to 1. Uh, in general, it is not true, but because sequence of probability distribution functions need not converge to a probability distribution function. But yeah, there is a proof which says it shows that this summation pi j equal to 1, which we'll not be doing here. So we'll be proving the uniqueness of the solution pi equal to pi p, assuming that pi there is a solution pi equal to pi p and summation of pi I equal to 1 for every k. So yeah, we'll show that. So the second one will show. So pi equal to pi p and summation of pi I equal to 1. Now we know that since pi equal to pi equal to pi p power k, right? And now we can take the average. This will still remain pi. And this will go pi 1 by n. Take limit n tends to infinity on both sides. So this is pi. And since it is the limit, the pi is unique. Right? If you have a sequence and converges to a limit, then that limit is a unique limit. Okay, so this is the proof for uniqueness. And if this was transient or null recurrent, then this would converge to 0. And if it converges to 0, then you'll get a contradiction. Okay, so yeah, that is it for today. I'll stop the recording. And in the next class, we'll do some examples of DTMC. And then in the next two classes, we'll introduce CTMC and also we'll do some problems in CTMC.